Welcome. So the purpose of this lecture is going to be to talk about limits as we go off to infinity and horizontal asymptotes. And this will give us some more tools that we'll be using to graph functions. So horizontal asymptotes. And limits at infinity. So let's start with a basic example. Let's imagine that we have some function, and let's use just some simple example, 6x minus 1 over x plus 3. And let's suppose we want to ask the question, what happens as x gets large? What does this function tend to do? So if we plug in some large value in for x, I don't know, let's take 100 or something like that, so x equals 100. Then what you can see is what we get. We get 600 minus 1 on the top over 103, so 599 over 103, which is, well, whatever this is actually pretty close to, if I just had 600 over 100, it's pretty close to 6, actually, right? Pretty close to 6. And what you can see without too much imagination is that if I were to continue in this way, plugging in bigger and bigger numbers, then the result that I would get would be closer and closer to 6. We're going to eventually formalize this by writing the limit as x goes to infinity of 6x minus 1 over x plus 3 is equal to 6. Okay, so what I'm going to do right now is going to be broken up into two sections. The first thing I want to say is, what does this actually mean? So let's see if we can be more precise about what we mean to say when we say the limit as x goes to infinity is something. And then we want to come up with some tools for computing such limits. And we'll then eventually put that together to be able to look for horizontal asymptotes of functions. So so if we were to look at this particular example and make this observation that as x gets large, the values get closer and closer to 6. The standard graphical interpretation of that is that if I were to look at the y value 6, well, I haven't really said in what way I'm getting closer to 6. Maybe I'm increasing towards 6, or maybe I'm decreasing and getting closer to 6. But the point is that as x gets bigger and bigger and bigger, what we know is that we get closer and closer to this line y equals 6, or at least that's what we suspect from just our heuristic analysis. Okay, so these limits have to do with horizontal asymptotes. Let's get a precise definition going now. So we say that the limit as x approaches infinity of f of x equals L to mean that we can make f of x as close as we want to L if we make x sufficiently close to, sufficiently large. So we saw this concept at one point before. The question is, what does it mean for x to get close to infinity? You know, this is just a colloquial phrase, if anything. But what we interpret this as meaning is x getting sufficiently large. So by making x as large as we want, or as long as we need to, as large as we need to, we can make our function as close as we would like to L. And similarly, one can talk about limits as x goes to negative infinity as well. So if I had a minus infinity, what does that mean? That just means as you go off on the x-axis to the left as far as you can. So this says that if the limit of f of x is L as x goes to minus infinity, this means we can make f of x as close as we would like to L if we make x sufficiently large negative. That is to say, sufficiently negative, sufficiently towards the left hand of the x-axis. Okay, let's go ahead and compute some of these limits just to get some practice. The basic fact that we're going to use that's going to let us compute these things is that the standard limit laws that we learned from before still apply to these infinite limits. So that is to say, suppose you have a couple of functions, and you know that one of them, as you go off to infinity, approaches L, and the other one approaches M. Then what do you know? You know about the sum, the limit of the sum, the limit of the difference, the limit of the product, etc. All the same rules apply. I'll just write a couple for demonstration. So I'll just say same limit laws apply. So for example, in particular, we have the limit as x approaches infinity of f of x plus g of x is going to be the sum of the two limits. The limit of a product is the product of the limits. The limit of a difference is the difference of the limits. And for example, if we have a limit of a quotient, this is going to be L over M, provided that M is non-zero. You don't want to divide by 0 or come close, and so if M is 0, we do not use that limit law. That limit law doesn't apply. Okay, etc. And the other standard laws apply as well. Now, this, combined with one extra fact, is going to give us a lot of traction. So to kind of do any good computations, we need one additional fact, and that is that the limit as x goes to infinity of 1 over x is equal to 0. This is the statement that if you have a number which is small, which is big, and you put it in the denominator, then the fraction gets small. 1 divided by big is small, is what this conceptually says. Now, if we take this fact together with the limit laws, we now have tools to compute a whole bunch of interesting limits. So let's do an example or two. Well, how about we start with something like what we began with, like 6x plus 1 divided by x minus 3, for example. And we would like to compute this limit. We would like to make use of our fact, and the one simple way to make use of that fact is to try to rewrite this to involve 1 over x's instead of x's. The standard trick to do that is we multiply both the top and the bottom by 1 over x. So in this example, when I do that, distribute that through, the 6x turns into a 6, the 1 turns into a 1 over x, I get a 1 minus 3 over x. And now I use my limit laws one at a time. This is going to be a limit of a quotient. I can write that as a quotient of the limits, provided the bottom limit isn't 0, which we have to check and make sure that that actually holds. And the limit of the sums and the differences, I can distribute the limit over that. And so I get the limit as x approaches infinity of 6, plus the limit as x approaches infinity of 1 over x over the limit x approaches infinity of 1 minus the limit as x approaches infinity of 3 over x. Now, all these pieces I can evaluate very simply. A constant just stays by itself. I mean, as x gets close to infinity, 6 gets close to 6, because it's 6. 6 is 6. And so I get 6. I have a 1 from this limit. And now, the 1 over x, if x goes to infinity, our fact tells us that that's 0. For this 3 over x, well, maybe it's easier to use the constant multiple rule and pull out the 3. And then I know that this is minus 3 times 0, and that'll give me a 0. The answer is 6 over 1, which is 6. Just as we suspected, we get the answer is 6. Okay, and that's the basic idea for how these things can be computed. Maybe one more example, just for fun, is the limit of about 2x squared minus x over 3x plus 1. Again, we have this problem of having these x's. I'm going to multiply the top and the bottom by 1 over x. Multiplying the top and the bottom by 1 over x is going to not fully fix the top, but it will at least get rid of the x's in the bottom. So let me just see what that does for us. So in the top, when I multiply through, I get a 2x minus 1. And in the bottom, when I multiply through, I get a 3 plus 1 over x. So the denominator, if x goes to infinity, this goes to 0 and it gets close to 3. So the limit of 1 over x, remember, goes to 0. The top, well, 2x gets big. The 1 doesn't help things that much. The top gets big. So colloquially speaking for a moment, this looks like big divided by 3, which is big. This limit's actually going to go to infinity.